Hi, I'm Corey Kell. This week's presentation, video 2.1, is the 45-degree sector test, the definitive test when testing Earth's surface shape. And we're going to talk a little bit more about that as we go through this presentation. Why we use the sun in the 45-degree sector test. Now, I'll go over the test box and the text box worksheet, what was created in order to test Earth's surface shape and find out whether or not we're measuring the sun's height from a flat surface or a curved or spherical surface, and what that difference is and how we can determine that. The sun, why do we use the sun? Because the sun is the center celestial body for the globe model, so that's kind of the obvious. That's why you would use it, because it is the center celestial object. The Earth and the other luminaries orbit around it in the heliocentric model. The equatorial plane and tropics is the sun's operating range. It kind of carves out lines on the globe, or the globe model. That's the sun's operating range, so we can't that's very definitive, and those lines are on the globe model where that sun's operating range is as the globe spins for that model. It creates those linear, or those lines. The greatest factors influencing testing, we talk about vertical angle as distance, and elevation. We'll get into a little bit about that and show you how that works. Higher angles exclude lensing and refraction. Why we do the 45-degree sector test. This comes directly out of military science practices. How we can exclude that refraction up at 45 degrees or higher angles. If we get below 20 or 25 degrees, then we get that lensing and refraction occurrence. The definitive test, testing during the summer solstice. Why we test during the summer solstice? Because the sun is the closest up in the northern hemisphere. And during that summer period, that's when you want to find out whether that globe model meets that requirement, if it can pass that test, that vertical angle, which is the definitive test. Military science being one of the major backgrounds where I pulled this application of. It is a higher knowledge. It's not taught in traditional education, and it has real-world practical applications. Again, using height measurements, and when we specifically talk about that, we're talking about measuring sun height. Again, coming out of military science. We'll talk a little bit more about what military science is. It's quite a lengthy definition, but this is kind of it in a nutshell, and I think this comes from Wiki. And this is only part of it. It's a very large definition, but this is kind of the meat and potatoes of it. Military science, the study of military processes, institutions, and behavior, along with study of warfare and the theory and application of organized coercive force. It is mainly focused on theory, method, and practice of producing military capability in a manner consistent with national defense policy. Military science serves to identify the strategic, political, and economic, psychological, social, operational, technological, and tactical elements necessary to sustain a relative advantage of military force. Whew, that is a big sandwich definition. There's a lot going on in there. People always just tell me, well, that's not military science measuring sun angle. Oh, it absolutely is. And that's when we talk about geometry, because geometry is built into military science. And when we specifically talk about that, we're talking about positioning and measuring angles, or vertical angle, measuring heights. And that directly relates when we get into celestial bodies and survey operations. So those three main areas, those practices and applications, were pulled out of the military science, which is huge. It's absolutely huge. The test box. The test box, this is kind of a naked test box with nothing in it. But as you can see, this is a 3D version of what the test box actually looks like. And this is very simple, very doctrinal, simple geometric form. But it can be used and has excellent application and practice once we start to build information and requirement into it. And once we do that, this is kind of what it looks like for the 45-degree sector test. As we talk more about that, it is a specific, very technical test. It's a very technical test, but it's a very simplistic test. So it's kind of best of both worlds. And we need to understand that we're measuring the sun height from when we set out using the sun. We put in a sun survey point at the OS or the orienting station location, and we get on manual vertical or manual linear alignment. This would be sun position 1, or what's called solar noon at this position. So based on where we at on Earth, we are linear on line, and here you'll see that we're using 90 degrees because the sun is always 90 degrees up in the summer or at the equator during the equinox. That's one of the reasons we can do that. We get a very clean angle. And then 3 hours, or we break down the globe model into 45-degree sectors, which 8 times 3 is 24. So at 3 hours, our sun position should be 45 degrees. Or that's built into the 45 degrees, or giving us a 360 degree circumference as that model orbits orbital rotation. So part of that, we break that down into sector of 45 degrees, and that distance, we can verify the distance based on a sun plot methodology, and we'll talk a little bit more about timing in a different block of instruction. But the sun plot, and this is a position to the sun's 90-degree position in the tropics, and we can calculate that by using a measured azimuth to that position based on the sun. The best time to do it is during the summer solstice, because we know where the sun is at in the northern hemisphere on the Tropic of Cancer. So we can get an exact position, measured azimuth, and we can get that exact distance of 45 degrees. And then at that desired sun plot time at that time, or 3 hours, based on which methodology we use, we get that vertical angle, or that sun height, measure that sun height. And remember that the limit is always 90, because the sun is always 90 degrees during the summer sun season. And that's why the limit on vertical angle is 90. So we need to have, but when we're using the globe model, we need to include that distance, which equates to surface angle and then sun height. So those two numbers have to add up and be less than 90 or less for the globe model to pass. Where this was derived out of was military science, live fire safety boxes. I covered that in one of the other videos. Here we see that this position, this artillery beast, is firing indirect fire into a safety box, which is located inside the impactor. We have our left, right, near, and far limits, which create a box. And all that is these are lines of parallels or limits. So as we build this 45-degree sector test box developed from this, as you can see here, all we're doing is we're placing that box. That is a box that would fire live fire artillery rounds in safely, that they can impact where they won't, where they hit the target in training, and they're safely fired in this area. Test boxes is kind of the same thing. It has limits. It has definitive limits, and that's how I developed it. It comes right from these defining limits, and this is a direct application and process from the field of military science. I talked a little bit earlier about linear manual alignment in the test box. This is kind of how we achieve linear manual alignment. Whether you believe we're on a globe or a flat Earth, we're going to use we use what's called a compass and a marks device, and we get our solar noon position to magnetic north, or our linear manual alignment, when that sun comes on a line. And of course, if the sun is between the equator and the Tropic of Cancer up in the north, that's our summer sun season. If the sun was out of this season, then we'd be in fall or winter, as if it moves towards the south in the Tropic of Capricorn and the equator. But this is the sun's operating range, this belt or this band. And you can see here that's goes around. That's, a lot of people say, well, that 90 degree doesn't exist. Well, that's absolutely false, because we have these lines. The Tropic of Cancer, the equator, and the Tropic of Capricorn, they're definitive. So that is absolutely incorrect. So the sun being at 90 degrees, these lines delineate that. That's proof or evidence of that existence. Again, linear manual alignment. Once we get that linear manual alignment, we can break that down into sectors for either model, the globe or the flat Earth model. And all we're doing is, once we get that manual alignment, 3 hours, we measure across sector and get that vertical angle. As we see here, we're broken down into 45 degree sectors, or 8 sectors for each model, whether you're testing the globe or the flat Earth model. Very definitive, very exact science, and very accurate. This kind of leads us into once we do that measurement, we get that information. We get the observer angle for the globe model. Remember, observer angle is the distance between you and the sun plot, or the sun's 90-degree position. So if you're doing the 45-degree sector test, this will be 45. If you're measuring the sun height at 3 hours, or the designated sun plot, and this would have to be 45. 90 degrees being the limit to pass for the globe model. So all you're doing is just adding these two numbers. The flat Earth model has a huge advantage in this. Observer angle is always 0 because you're not on any curved surface. You're level when you're measuring it for the flat Earth model. And then all you're doing is simply measuring the sun height. So you got 0 plus whatever your sun height or vertical angle measurement is. So you can get up over 60 degrees easily with this model. Huge advantage, and all you're doing is adding those two numbers together to get the sum total. And again, 90 degrees being the limit, or 90. Here are some examples, and again, this is kind of a review what we talked about the other week in the test box worksheet. And all you're doing is filling in this information: the observer angle and the measured vertical angle. And all you're doing is adding them together. Remember that the limit 90 because the sun is always 90 degrees. So anything 90 and below would pass for the globe model. This one here, we have 42 and 45. This would pass. This example where we have 45-degree sector test, measured 52 degrees, so that total would be 97. This would be a fail, or a fail by a number of 7 or 7 degrees. So that would be a fail. And these are the test box example for the worksheets for the flat Earth model. And you can see that this is just a straight line across 0 degrees surface angle, and then the vertical angle number on top, both passing easily. Again, huge advantage. You have a long ways to go up to 90 degrees. You can go well up above the 60 degree range, especially if you're doing the 45-degree sector test. This builds into what Copernicus would have had to done, again, because the sun is the center celestial body, and the Earth and the other luminaries are said to be orbiting around in this galaxy of this model, so the heliocentric model. So again, if we look at that model, those lines on the globe, if we take a look at any globe model, it always has these lines: the equator, Tropic of Cancer in the north, and Tropic of Capricorn in the south. That delineates, as this model spins counterclockwise, it creates those linear lines on that model. So that is an exact process for that model, and that's again why we use the sun, because it is the center for that model, and that's why military science uses the sun for survey applications. It can be used to find exact locations and positioning. It's very accurate. Again, what I talked about, those lines on the globe model, it creates those lines. As the globe spins, it creates those lines as that sun is on alignment with the globe. Whether it's in the what they call the elliptic or the elliptical order that sun is tilted, you have to look at the Earth to sun relationship. So when there's zero declination when the sun is during the equinox at the equator, so that alignment, there's no tilt or no angle between those two celestial bodies, and then you get the tilt of 23.4 or 23.5 degrees to get summer or winter based on what your location and what hemisphere. Again, huge problem for the globe model. It actually works against that model. The two greatest factors in testing, what we need to understand, as elevation and distance increase, you get measured sun angle will decrease. So the closer you are to an object, the higher sun angle, the higher measured angle you're going to get to that object. Same thing with elevation. As elevation is lower, you're going to get a higher measured angle reading. So it kind of worked just the opposite, and we'll show you examples of that. And here we have, you see the effect, because we need to understand that effect. That will affect our measured angle readings, our vertical angle readings. Here we have an observer farther out from the sun or the object, getting 35-degree vertical angle reading. Here, the closer the observer is, they get that higher vertical angle reading to the sun, and that 90-degree angle, that's the guide angle. And that's effect of distance. Elevation, same thing. We get that same effect. So the higher we are, to the higher in elevation we are to that celestial body or that elevated object in the sky, the sun, the lower the sun angle, the lower measured angle you're going to get. If you're down at sea level, you're going to get the higher vertical angle measurement. So the lower you are in elevation, the more higher you should vertical angles should be. During ORT resolute time, I was at a elevation of over 5,000 feet. We should have got really, really low sun angle readings, and we didn't. We got readings over 50 degrees, so that was a huge major failure for the globe model. Again, being able to identify that limit, the 45-degree sector test. 45 degrees is the limit. You're doing the 45-degree sector test, so if you get a reading of 46 degrees and above, that is a failure for that 45-degree sector test. Why? Because the high sun means that you're measuring it from a flat surface, not a curved or spherical one. Again, but you have to understand how to get that limit. And why? Because the sun's always at 90 degrees. The strategic and fundamental of accuracy of military science is vital. Because lives depend on its safe use and practice every day, and because second place in military science can get you conquered real quick. Real quick. We talked about refraction, or being able to identify refraction, and how military science has avoided refraction when we measure celestial bodies up at high angles or above 25 degrees. And this is our M2 aiming circles, and these are kind of like survey devices, but we use celestial bodies such as the North Star Polaris or the sun in the daytime. The military science has a star chart. I always liked using Polaris because I always kind of knew where it was, and I knew its star code, and it was always easy to find. But you can just about use any star, but Polaris is especially because there's really no movement of it. I think it's 0.2 mils. Very, very, very little movement in it at all. So I always like using it. But basically, how it works, how we know that there's no refraction at these high angles. We have two circles. The circle on the right is the lay circle, and the circle on the left is a safe circle. And what they do is they do independent different lays. So the lay circle may use the sun in the daytime, and then there's three primary methods of lay: oriented angle, or survey, or magnetic. And this circle would go magnetic. Once they orient, then what they do is they turn an angle on each other. They bump, or they look at each other. And when they bump, they have to be within 10 mils of each other. And I'll show you how that works using two circles. And then each operator will read a reading. And then if you're within those 10 mils, that proves that independent between the two different types of lay, that there is no refraction, or very, very less than a third of a degree, which is very minimal. So 99% of the time, the circles will be within 1 to 2 mils. And we can break it down, 17.8 mils in 1 degree. 360 degree circle is 6,400 mils. And again, this comes out of field artillery gunnery methods of lay. Again, very accurate, very technical, but again, very accurate and very definitive. And this is what I'm talking about when we talk about circles. The two circles bump. Here we have positioning, and there's a saying that if you see red, you read red. Well, this operator, he's looking in the direction of this operator. What he does is this operator over here will read, and he reads red 1600 back to this operator right here. Okay, he reads back to the safe circle and says 1600 mils. And this operator looks at his thing and says, yep, 1600, that's 0 mils. So these circles are looking, and this is called bumping. So this completes the triangle. And triangulation is very accurate, very technical, and very definitive. I know some people don't believe in triangulation, but if you've never used it in real-world applications, especially for survey, using celestial bodies and then bumping it against a different methodology, you'll have no idea. You'll have no idea. It'll be completely foreign to you. And that's not an insult to anybody's knowledge. It's just something that's not taught, again, in traditional education, unless you maybe get into survey. Again, very technical process, but very accurate and very definitive. And again, why that 45-degree sector test, why it's the limit, because as you go up, here we're sighting in on the sun, center mass, you have an angle above and angle below. As you continue up that line, that angle increases, that vertical angle. So if you're doing the 45-degree sector test, this is your limit right here. So if you get up 46 or above, up over 50, you're out of the limit for the globe model. And that's just simply how it works. It's a very technical experiment, but very easy to do. And once you identify that limit, you know that limit, you can't exceed it for that model. That means you're measuring, if you're up in that red zone, you're doing a 45-degree sector test, that means you're measuring it from a flat Earth surface. This concludes this week's presentation video 2.1, the 45-degree sector test. I'm Corey Kell, creator of Flat Earth Intel, and thanks for watching.